So our last topic in Unit 4 is oxidation reduction reactions, also known as redox reactions. So we're going to jump right in and talk about assigning oxidation numbers, how we determine whether something is or is not a redox reaction, and then we're going to talk about how we balance redox reactions. So let's pull this up. Oh, this way, sorry. Okay, so oxidation states and balancing redox reactions. So just a quick review, we know that an oxidation reduction reaction is one that happens when an atom or an ion loses electrons, and a reduction occurs when an atom or an ion gains electrons. They have to happen together. We can't have electrons coming from nowhere. So oxidation happens when one thing loses, reduction happens when another one gains. And of course, we have two different ways of remembering that. We can think about Leo says Ger, losing electrons is oxidation, gaining electrons is reduction. Or we can use oil rig, oxidation is losing, reduction is gaining. So if we want to keep track of where the electrons are, we need to assign something called oxidation numbers. And so we're going to talk about how we assign oxidation numbers. The first one is easy. Elements in their elemental form have an oxidation number of 0. So that means something like oxygen, O2, would have an oxidation number of 0. Or sodium, Na, would have an oxidation number of 0. If we have a monatomic ion, so this would be the sodium ion, Na plus, its oxidation number is the same as its charge. So anytime we have an ion, we know its oxidation number because it's the same as its charge. Now, moving on to slightly more complex ones. When we talk about nonmetals, they tend to have negative oxidation numbers. They can be positive in certain compounds or in certain ions, particularly the polyatomic ions. Specifically, oxygen is going to have, unless it is in its elemental form, an oxidation number of -2. So oxygen in a compound is going to have an oxidation number of -2, unless it's in the peroxide ion, in which case it has an oxidation number of -1. And the peroxide ions we recognize because they'll have two oxygens paired with two group 1 metals or potentially one group 2 metal, and they'll be named as peroxides. Hydrogen is going to be -1 oxidation state when it's bonded to a metal, or it could be a +1 when it's bonded to a non-metal. So most often hydrogen is a +1, but it is a -1 when it's bonded to a metal. Fluorine, in a compound, we're always going to assign an oxidation number of -1. So we have at this point now 3 rules about 3 elements, and we know how to assign oxidation numbers to elements and to ions. What about everything else? Everything else we're going to find based on the idea that the sum of the oxidation numbers in a neutral compound is 0, and in a polyatomic ion is the charge on the ion. So if we have one of those 3, oxygen, hydrogen, or fluorine, then we can assign those. Otherwise, we're going to find the most electronegative one, assign it, and work from there. So let's do a little bit of practice. In these elements, we have P2O5. Well, we know the oxygen is -2. So the total oxidation state over here is -10, which means this must add up to a +10 so that our species can be neutral. So +10 divided by 2 is +5. So the oxidation state of phosphorus here is +5. Here we have hydrogen with a metal, so we know that it's going to be -1. Here we have chromium with oxygen in the dichromate ion. So we're going to use our ions sum to their charges rule. So we have oxygen, which we know is -2. We have 7 of them, so that's a -14. Something plus -14 makes -2. So we know that this must have a total oxidation state of +12. So the chromium itself must be +6. Here we have tin bromide, and here we know that tin is an ion and bromide is an ion. Since the bromide is -1 and there are 4 of them, the oxidation state of tin is +4, and you've been doing this for a long time in determining oxidation states of transition metals. And here's our last one, H2O2. We see that we have 2 from group 1 and 2 oxygens, so we know that the name of this is hydrogen peroxide, which means that the oxygen is a -1 and the hydrogen is a +1. Let's put that into the context of a reaction. So let's take a look at these and see if we can figure out what's oxidized and what's reduced. So here we have the permanganate ion. We know that oxygen's a -2. There are 4 of them, so that's a total of -8. -8 plus something makes -1, so that something must be a +7. So we have a +7 here and a -2 here. Our hydrogen here is a +1. Our oxygen, since this is peroxide, is a -1. So our manganese here is an ion. It's a +2. So we know that it goes from a +7 to a +2, which means that it must have gained electrons, which means that it is reduced. Our oxygen goes from a -1 to a 0, so it lost electrons, so it's oxidized. So the manganese is reduced and the oxygen is oxidized. Now we're going to look at hydrogen peroxide, and this is a decomposition reaction. So we have a +1 and a -1. This is still a +1, but this oxygen is a -2. So this oxygen, one of these oxygens from the hydrogen peroxide, gained an electron. So oxygen is reduced. But we notice over here that we have pure elemental oxygen, which has an oxidation state of 0. So another oxygen must have lost electrons in order to go from a -1 to a 0. So oxygen in this case is both oxidized and reduced. Okay, so let's talk about balancing these equations. So we are going to use something called the half-reaction method. And when we use the half-reaction method, we treat the oxidation and reduction as 2 separate processes. We know they have to happen together, but we're going to treat them like they are 2 separate processes. We're going to balance each half reaction independently, and then we're going to combine them to get the balanced equation for the overall reaction. So first thing we're going to do is assign oxidation numbers to determine what's oxidized and what's reduced. So step 1, assign your oxidation numbers to determine what's oxidized and what's reduced. And step 2 is that we're going to separate it out into 2 separate half reactions. We're only going to write those species that are being oxidized or reduced, and that's our half reactions. Step 3 is going to be to balance each half reaction. So we're going to balance our elements other than hydrogen and oxygen. Then we're going to balance oxygen by adding water. We're going to balance hydrogen by adding hydrogen ions. And we're going to then finally balance charge by adding electrons. So 4 steps, to balancing each half reaction. Then we want to make sure that the electrons gained and lost are the same. So we're going to multiply the half reactions by integers so that the electrons gained in one is the same as the electrons lost in the other. And then we're going to add up our half reactions, subtracting anything that appears on both sides. So let's take an example. Oh, and we're going to make sure that the equation is balanced. Okay, so let's take an example. We have this reaction between the permanganate ion and the oxalate ion. And I'm going to move away from the PowerPoint and I'm going to have you guys watch as I go through one of these. Okay, so, all right. So here's our reaction. We have the permanganate ion and the oxalate ion and the manganese 2 ion and carbon dioxide. So our first step is going to be to assign oxidation states. So I look at my oxygen, I see that it's a -2. There are 4 of them, so that gives me a total of -8. -8 plus something equals -1, so I know this must be a +7. We come over here to the oxalate ion. Again, we know that oxygen is -2. There are 4 of them. This must be a -8. -8 plus something gives me -2, so this must be a total of +6. So each of these must be +3. Now over here, this is a monatomic ion, so the manganese is +2. And over here we have carbon dioxide. We know that oxygen is a -2. We can see that the carbon, therefore, since there are 2 of them, must be a +4. So we can see here that our manganese goes from a +7 to a +2. So we know that it gained 5 electrons. On the other hand, we see that our carbon went from a +3 to a +4. So we know that it must have lost electrons. So we're going to say that it lost 1 electron. Okay. So let's take a look, and we're going to separate this out into our half reactions. So my first half reaction is going to be the permanganate ion forming the manganese 2 ion. And my second half reaction is going to be the oxalate ion forming carbon dioxide. First thing I have to do is balance the atoms other than oxygen and hydrogen. So I have manganese, I have 1 manganese here and 1 here, so I don't need to balance anything. I have 2 carbons here, so I need to put a 2 in front of carbon dioxide to balance that part. The next step is to balance the oxygens by adding water. I have 4 oxygens on this side, so I'm going to add 4 water on the right side. I have 4 oxygens here, and I have 4 oxygens here, so I don't need to do any more balancing here. I have 8 hydrogens, so I'm going to add 8 hydrogen ions on this side. Now, all of my atoms are balanced here. All of my atoms are balanced here. Now I'm going to add electrons to balance charge. So we can see over here that we have a -1 and +8, so this is a +7. And over here, we have a +2. We can only ever add electrons. So we're going to add enough electrons on this side to bring the total charge on this side to the same as the total charge on this side. So we're going to add 5 electrons. And this is a stop and check point. We said before that our manganese gained 5 electrons. Right here, we see that our manganese is gaining 5 electrons. So we're good to continue moving on. Here, I have a total charge of -2 on this side, a total charge of 0 on this side. So I'm going to add 2 electrons here. And again, we're going to do the stop and check. Now, I said that it lost 1 electron, but that was each carbon that lost 1 electron. And there were 2 carbons, so we could say that this lost 2 electrons, and that matches up with what we have down here. Now, before I can combine these reactions, I need to make sure that I have gained the same number of electrons that I've lost. So I'm going to multiply both of these equations by an integer in order to get the number of electrons lost and gained to the same place. Well, there's no common, so I need to multiply this by 2, and I need to multiply this by 5, and that's going to give me 2 permanganate ions plus 16 hydrogen ions plus 10 electrons yields 2 manganese 2 ions and 8 water molecules. And I have 5 oxalate ions forming 10 carbon dioxide molecules and 10 electrons. So now we're going to combine these two reactions, and that's going to give us 2 permanganate ions plus 5 oxalate ions plus 16 hydrogen ions plus 10 electrons yields 2 manganese 2 ions plus 10 carbon dioxide molecules plus 8 waters plus 10 electrons. And now I see that I have 10 electrons on the left and 10 electrons on the right. So we're going to cross those out. And our final reaction is 2 permanganate ions plus 5 oxalate ions plus 16 hydrogen ions yields 2 manganese 2 ions plus 10 carbon dioxide molecules plus 8 waters. So that's how we balance in a redox reaction in acidic solution. So I'll go through